Well, good morning, everyone. Hopefully, everyone had a great weekend. Today, we're going to continue on with our discussion about droughts and critical water shortages in the United States. So, just a reminder, we talked about this in class on Friday. Um, you know, there are droughts are sort of continuously changing throughout the season, but as you'll recognize currently, just looking at today or last week's report, really, new one will come out on Tuesday. That you'll see that basically almost half the country by landmass is in currently in a drought, particularly some of the more highly populated areas on the west coast, and certainly the Mountain West is in a pretty prolonged drought that's reached pretty serious proportions. So, all together, the issue of drought is something that can be that gets intensifies with climate change. Um, so this is a switch up from our flooding to an area that's an absence of water. Luckily, Ohio is sort of out of the drought phase, and reasonably okay, but many parts of the country are in pretty severe drought conditions. And what we talked about last time, just to review, where we ended up was really talking about the drought in California. Uh, Remember there that most of the onset of drought in that region is actually caused by declining snowpack in the Sierra Nevada mountains on the eastern side of the Imperial Valley, or the Great Valley in California, which have declined over years. And as a result of that declining ice mass, you've actually observed that there to be significantly less water melting in the ice mass, flowing downhill into the reservoirs, which are actually used in the California aqueduct system to provide water to locations like San Francisco, LA, and all the places in between, as well as for agriculture in the Imperial Valley. Just to highlight some things that are important there, just remember that relatively recently, within the last decade, that legislation governing groundwater use has been enacted to sort of handle this. It's largely because in that region, in instances of drought or even dry parts of the season, one of the best mitigative efforts is actually to switch over to using groundwater. Of course, groundwater is in the subsurface by definition. Means it can't be evaporated, but it can be drawn down. And we talked about this, and just to review from last week, is that there's many locations, in fact, throughout the entirety of the Imperial Valley, many locations where the drawdown of the water has reduced the fluids that are filling those pore spaces between sediments in those areas, and you're actually seeing pretty rapid compaction and sinking of the land surface, in those areas because water's been removed. So, as we mentioned before, this can cause problems with infrastructure, can actually ruin irrigation ditches, can cause problems with not just water infrastructure but power lines, things like that. And that subsidence is sort of going on today. The key thing I wanted to stress again about the subsidence issue is that it's not just as simple as, okay, we let the water get drawn down and we put water back in. Once this compaction occurs, or subsidence occurs, the spaces that ordinarily would have water in them have actually been reduced to smaller and smaller pore spaces, and the result, you can't actually reinflate the aquifer. I've given you this example in terms of California, but many parts of the agricultural belt suffer from some really serious concerns related to subsidence, which we might talk about a little bit later in the semester, in areas like the High Plains aquifer in Nebraska, Kansas, etc., on the east side of the Rocky Mountains. They suffer from the same issue where water's been accessed from groundwater. The removal of groundwater has drawn down the aquifer, but also led to subsidence, compaction, and basically in those areas, it's not really feasible to get more groundwater in because the pore space has been gone. So many implications for groundwater, for the future groundwater recharge here. But the biggest one is that subsidence will change the storage capacity of water and of the ground water, and as a result, the implications will be quite profound in terms of minimizing the potential for water to recharge. As a result, there's no future water resources in those areas. So what we're going to pick up today is continuing to go on with some of the other risks related to groundwater drawdown and drought. Not so explicitly related to groundwater, but drought in the region actually causes, not surprisingly, a series of factors. One of them is related to the increased risk of wildfires. This is actually the Valley Fire from 2015, but if you've been watching the news in the last, several months, there are plenty of concerns with forest fires ongoing in the region. The basic premise is during drought conditions, you're not seeing as much vegetation. Vegetation is there, starts to dry out. In severe drought, as we talked about in the last class, you can actually see the vegetation start to die. And the result of that dried out or dead vegetation is that it actually becomes fuel to catalyze fire. So it doesn't take much for a fire in the area to start. When it does, it can spread pretty rapidly because the drought related dryness causes that vegetation to basically serve as burning embers. So just this is perspective of the 2015 one. They're still collecting data on the runs from this year, but these you've seen in the news pretty regularly throughout the last several years. These can burn immense amount of areas. 75,000 acres is not at all the biggest fire we've had now at this point. Displaced 13,000 people. Consumed over 600 homes in this particular example, and amazingly only 3 tragically tragic deaths. So are there other factors that have increased the risk of wildfires in addition to drought? I mean, that's a fair question. Again, it goes back to all the other aspects of water and drought related things we've talked about, is that you've seen land use change. You've seen increased electricity demand. So there's power lines that are out there that can be, if broken in a storm, can touch down and cause a fire. That's been one of the recent events. But everything related to land use change, related to deforestation, have sort of actually perpetuated this, as well as the fact that, quite frankly, as population growth has expanded, talking about from a sustainability perspective, that population growth is often going into more beautiful locations, into valleys and ridges in the area, and as a result, you actually can observe the scenario where there's more people living in densely vegetated forests, or previously densely vegetated forests, all which increase the likelihood of interaction between sparks and the forest, which can sort of increase the likelihood of wildfires. So the question I have here is, this improved? I think the events of the region the last few months even suggest that probably it hasn't improved at all, and in fact there's ongoing fires today that are of important risk. Some other factors. This is just showing you it's not just ground mass ferns and grasses at the bottom that become affected. These are actually some evergreen trees in the region. This is 2003, so early part of just at the turn of the century. Within 10 years, based upon that prolonged dryness from about 1999 up to 2017, they started to lose significant portions of the forest based on the fact that the water table was drawn down. There's no longer access to surface water because of the drought, and major forests can actually be lost. And you can probably understand implicitly the risk related to losing forests like this, lack of CO2 sequestration and formation of oxygen, changes in habitat, changes in space for for migratory birds and animals. But one of the factors I'm just going to highlight here, just some of the unintended consequences maybe you all haven't heard about too much, is it's actually led to a major scenario caused by bark beetles, where the bark beetles were always there. They're actually an important part of the ecosystem. They fill their role, but typically speaking, in cold, particularly wet winters, the bark beetles populations are kind of minimized. A certain amount survive, and there's a balance between the bark beetles and how much damage they do to trees. Of course, when you start seeing warming temperatures, shorter winters, and particularly dry winters, there's nothing that's really held the beetle population back except for trees. And as a result, that's actually an example of something caused by drought, and climate change together, where the beetle populations have soared. In many cases, increased by about a factor of 10, and now drought-stressed trees are really susceptible to attack, and actually to tree death following attack. And this is exactly what we've seen, that the bark beetles have seen a great drop in the bark beetles have seen a great increase in their population, while the drought-stressed trees have been really susceptible to attack, and actually, in many cases, the trees haven't made it. They've further exacerbated those tree deaths related to the drought itself. So this is actually something that's led to pretty broad damage across almost all of the western, Mountain West and California, Pacific coastline. Many of the evergreen forests in those regions have been pretty severely affected by exposure to the bark beetle, and as a result, we now are actually seeing evidence of the bark beetle even getting further east, into parts of the northeastern United States in some cases where there's concern this is going to continue to move on. So, some of the things you don't think about related to drought, but can have pretty profound effects to the ecosystem. And you can see here on this map, the red is 50 to 100% damage to trees, with significant percentages of loss. So there are areas that have yet to be affected, haven't really experienced climate change to the same extent, but you can get the impression about just how important this can be related to sort of drought-induced climate change. So, okay, with the trees, what's some of the issues here besides just the changing ecosystem? We disrupt the food web. The pine cones are an important thing for food and for squirrels and bears. Obviously, you lose recreation sites, your real estate impacts. The economic impact is really great. The soil now is no longer held in place, and there can be rapid erosion due to the absence of trees, which can cause the soil to erode away, which decreases the likelihood of having recovering those forests in those areas. So when people talk about the impacts of climate change, or even specifically impacts of drought, you can recognize there are many pretty severe long-term implications that are have sort of immeasurable costs in many ways. So I already alluded to this, but as the climate continues to warm, droughts continue to intensify. The prediction is that the forests like this will continue to shrink. That'll obviously help. Will not help the CO2 picture, and as a result, it's a sort of a negative feedback loop where you're going to see the CO2 being absorbed from the atmosphere less frequently, and the problem will probably continue on. So, just from historical perspective in the region, talking about sort of like long-term drought versus water usage in the area. This is actually a metric called moisture balance, and that basically, if you stay at zero, that would imply, over the long term, this is from 1000 AD to 2100 AD with model projections over here in the colored areas and real data here in the last handful of years. What's important about this is that if we stay very close to zero, it implies that we are using about as much moisture as coming into the system. So this is, you can think of this as Nebraska or Kansas. You can think about this as Southern California. And you'll note before the populations of those areas increased dramatically, even as they started to, we actually saw for quite some time that the population was staying roughly in balance with the moisture inputs from precipitation in the region. But what we've actually seen, particularly on the turn of the century around 2000, is that the reality is that both areas experienced pretty big departures from an adequate moisture balance, where particularly in the southwest, we've seen drawdown in aquifers, we've seen overuse of snowmelt, and basically there literally isn't enough water to go around. And both the actual data and the projections are suggesting we're heading into a time where there's going to be an imbalance between moisture, for agriculture, drinking, power generation, et cetera, in those regions. Basically, in areas that one of the things I want to highlight, we'll talk about this more as we go on in the semester, is that both these areas, most of the water is actually being used for agriculture. As we'll talk about as we move on, the biggest consumptive use of water in the entire world, and pretty much in any country of the world, is actually growing food. And these are the two most important agriculture regions of the country. So basically, in the absence of increasing moisture content, more storms bring more precipitation to the region, the long-term fate of these areas is fairly bleak. And there are actually pretty stark warnings about the potential for these regions to be in 50-year or 100-year limits to actually having viable access to water in those areas, which is important because of the sort of bread basket and the food basket of our country. So, in the other side of this is that there's actually a series of feedback loops from climate, ocean dynamics that can actually potentially, change the number of storms. So one of them is actually, those are sort of feedback loops that can change that drought scenario. But what we're going to do before we discuss those, potential things, because quite frankly, we don't understand them incredibly well, is actually talk a bit more about the natural system related to El Nino and how that actually is the main factor that controls droughts or precipitation monsoons in this region. So I think we talked about this a little bit earlier in the semester, but this is the monsoon is which kind of comes from the equatorial area of the Pacific and moves up into the desert Southwest, California, New Mexico, Arizona, is what is the sort of a seasonal stretch of the year where these monsoons move forward in El Nino times, are what is basically dictates the rainfall in the region. So just to remind you, or introduce it again, basically the key aspect here is that along the western coast of the Central and South America, there's actually what's called Walker circulation. It's what causes the trade winds to blow west to east, or what drives the very consistent flow of the trade winds more so. Directionality is controlled by the Walker circulation. And what that does typically is it actually causes the wind to blow east to west. So basically from Central or South America towards Tahiti or towards Australia, depending on where you're at. And what that does, if you remember back a few lectures to our ocean processes lecture, is that wind will actually cause waves, and those waves will cause the water, of the surface waters in the region, to move east to west. So that east to west movement of the wind and water will cause the water to sort of mound up, or actually there's topography to the height of the Pacific Ocean. It's not entirely flat, and it's not as, this is shown with great vertical exaggeration here. It's not tilting that badly. But going back to the ocean process lecture, that scenario of wind and wave action from east to west allows cooler, nutrient-rich waters to sort of pond up, upwell, along the coastline of Central and South America. That's important for fisheries and nutrient production, like we talked about. But that also means that most of the warm surface water is over towards Australia, over West Tahiti, and as a result, there's in what's the typical La Nina times, there's warm, wet, low pressure systems in the Western Pacific, and they are a big part of driving the monsoons and activity in that region. The alternative scenario is that on the opposite coast, I should say, is that cool water tends to have relatively low rates of evaporation, great for nutrient delivery, for primary productivity, and for CO2 drawdown. But in the La Nina scenarios, you don't actually see major amounts of evaporation like you do in the west side. This is occurring over here. In El Nino times, which there's variability. There used to be, when I was taking this course in my undergraduate days, we were taught it was basically about a 1 in 7 year cycle, where this process would sort of flip. The warm water would be over towards the eastern shores of South and Central America, and the heat and evaporation would occur very close to this coastline. And when those cloud systems form on the eastern margin of the Pacific, those systems will eventually move like cyclones away from the equator, and eventually, with the Coriolis effect, will crash in North America, and are important in those episodic years for providing massive amounts of moisture delivery to places like California, Arizona, New Mexico. The issue that's happened in California is for about the last nominally 20 years in Arizona, New Mexico, is that we actually haven't had a very strong El Nino. So there's sort of two competing theories. One is that we haven't had very strong El Ninos, and this second one is more a hypothetical situation, but where the El Ninos have occurred, potentially in light of really rapid evaporation, the El Ninos migrated further to the north, and most of the precipitation's gone up to sort of north of California, around the region. So I'm not totally clear if that's accurate yet, but the key aspect here is that when this normal system of the Walker cell driving wind and waves from towards the western part of the Pacific, when that does not occur, that's when we flip into an El Nino. It's called flipping to an El Nino. It used to be about once in 7 years. It's been a longer period to have that now, and as a result, there's no longer that episodic delivery of really massive amounts of rain to the California area. So this gives you perspective. In a normal year, this is 1997. The wind and waves sort of push all the way. This is the warming phase of the El Nino Southern Oscillation, or ENSO. This is where things are going well, or going normally, I should say, where wind and waves were being driven to the west. And you can see here this weaker pattern this is where this isn't happening as efficiently and can lead to more warmer waters in this region, which can actually cause some precipitation to make its way up into our neck of the woods or into southwestern United States, is next to the woods of Mexico, etc. Um, so the normal or the La Nina phase is typically when warm water is being driven out into the Pacific and really leads to wetness in Southeastern Asia and Australia. When it flips to El Nino, this is going to be sort of broken down, and more of the warm water is going to stay where it is or just not be mounded up. And all of this process together is called the El Nino Southern Oscillation cycle. But the El Nino that you think about is when the warm water stays over here and leads to precipitation that reaches the southwestern United States. So NOAA, which is the National Oceanic Association for the United States, classifies El Nino as periods where there's 3 months or more of warmer than average temperatures by at least a half degree in this specific part of the Pacific Ocean. So normally warm water would be pushed further over here. We monitor this area pretty regularly to determine if warm water is not getting where it needs to be, and if it's warmer than average, we can see very wet years. 2015, showing this the diminished La Nina phase was actually a situation where it was about 1.7 degrees hotter than expected, which is more than 3 times the temperature expected in that area. And again, one maybe 1 in 7 years used to be the average, but it's irregular, it's unpredictable. Often, in addition to the temperature measurements of the surface waters, historically people would sort of predict the Farmer's Almanac kind of level of prediction, would rely on like fisheries and off the coast of South America and Central America to make predictions based upon adequate upwelling, leading to primary productivity, leading to the fish sort of activity in the area. But this process is now is admittedly quite irregular. It can flip on a 1 or 2 year up to 7 year basis. Basically from 1999, really 1996 to 2015, it actually was in a La Nina phase, and there wasn't very limited water in this region, which is actually kind of what we're back to now. So in this area, this is called the Nino 3.4 region, which is the area where they monitor the temperature. And I won't test you in those details, so don't worry about that specifically. So so for perspective, 1995, 6, and 7 were some really prominent El Nino years, the strongest El Ninos I think that I recorded, unless there's something brewing now. But these are some of the strongest El Nino years, and actually rainfall in California was actually twice as high as normal. And in fact, you saw the southwestern part of the United States, coastal California, Oregon, etc., go into very wet periods. And actually, that leads to both precipitation in those areas. It leads to snowpack in the Sierra Nevadas, and it actually led to groundwater recharge in the Imperial Valley. Notice that the Great Plains during that time actually were, a big concern for precipitation. But the problem with sort of basing major population growth and major agricultural activities on that water axis, like we have actually done, we're running this experiment in real time in the United States, is that it's just not predictable. We don't know, 1 in 7 years is an average. It can be every other year, as it was in 95, 96, and then 97, 98. And as a result, it's really hard to build long-term infrastructure for housing, for agriculture, for industry in a region where you don't really know if your reservoir is going to be refilled this year or not. So overall, when you have El Nino, even when you have the El Nino, nothing's guaranteed to lead to twice as much precipitation in the area. But overall, there's more storm development in that region during that time. And actually, you see often more snow cover during those regions at the time. I know I was in high school during that stretch, and even though El Nino is predicted to only have light impact in central Pennsylvania, that was actually the snowiest. 95, 96 during a prominent El Nino, the strongest El Nino actually was the snowiest year in the recorded history of Pennsylvania, where we missed, we had several weeks off for major blizzards that came through. So it can be quite profoundly important. Importantly, between that 97, 98 year of an intense El Nino, all the way up through basically 2015 we had a strong El Nino again, but the moisture was brought further north. This part of the desert Southwest, central Southern California, Nevada, Four Corners region, actually had a prolonged period of extensive drought to the point where water aquifers were drawn down, immensely. Um, and really, I should state that I'm focusing in California because of the drought implications, but the same factors of El Nino and La Nina are relevant along the whole part of the West Coast. So this could affect not just drought in southwestern United States, but also can greatly affect things like fisheries and primary productivity all along the west coast of the U.S. up to Alaska and even into the Aleutian Islands and whatnot, where it can be warmer than expected, lead to more storminess in those regions, but also greatly negatively influence the fisheries and primary productivity in the region. In essence, what ended up occurring here, I'll sort of skip over this relatively quickly, is that throughout California we actually saw prolonged dryness, the north, central, and southern parts of California. Many of the areas were significantly below the rain production. The reservoirs, as we talked about earlier in the lecture on Friday, were drawn down, and basically going into the 2016-2017 winter, around the end of 2016, there were major concerns about how we were going to actually get water to the southwestern part of the United States. There were discussions about taking water supplies from other areas and actually building pipelines. Great Lakes. I mean, these are all conversations that never got serious, but there were discussions about moving Great Lakes water out to this part of the country because there was just really no certainty where things were going to go. And as I mentioned, showed you a graphic like this prior to in 2015, 2016, most of the reservoirs are down in the few percent to 20% kind of range of capacity filled. Luckily for California, in many regards, although we'll talk about some of the ways this was a mixed bag, many of the areas sort of benefited from the fact that 2017 became one of the, particularly early to mid-February of 2017, became one of the wettest periods on record for California. El Nino switched on pretty prominently, and that strong El Nino drove major storms, providing multiple years worth of rain really to California in a pretty short period of time. The positive aspect of that, of course, is that we actually had many of the reservoirs fill to capacity. We had many of the reservoirs fill up to their historical averages all in one particular rainy season or above their historical averages. The downsides we'll talk about is that some of these reservoirs actually exceeded their capacity and had some issues, as well as many of them, infrastructure is not necessarily equipped, as we talked about with flooding, to get all the precipitation at one time. And as a result, there was a lot of damage of infrastructure because of this. So, the key thing here is that as these reservoirs, which had actually been progressively getting drawn down and drawn down and drawn down, they were experiencing their own compaction. They were experiencing, changes in soil moisture and vegetation and whatnot. And then all of a sudden, when you take these major pulse of precipitation, it was great for filling up the reservoirs, but it actually led to major erosion and in some places collapse of the reservoir walls, as well as the sort of the flowways of the aqueducts that got damaged because they went to handling so much water so quickly. So this will give you a sense of 2015. The spillway was flowing down to the Feather River, and there was no thought about what we would do with too much water. Most people were entirely focused on major water shortages in the region at the time. But as you can see, here's the Oroville Dam Road. Here's the emergency spillway, and then basically by 2017, when El Nino switched on, when the precipitation, started to be fall pretty rapidly, Lake Oroville actually overflowed. The emergency spillway was flowing at a high rate for an extended period of time, several days, and actually it led to significant erosion of the spillway. Completely wiped out and eroded the road for the Oroville Dam Road, caused flooding, erosion and sediment deposition all across the region, heading down towards the, down in this valley towards the Feather River. And the spillway was just basically had to be left open to minimize the damage to this area. And the spillway actually, produced, basically had an incredible volume of water flowing through for a period of time. The spillway itself was actually damaged by the amount of water that came through it, where basically, the erosion and that came from off screen to the left here, over in this area, cut through to the spillway, wiped out the spillway, and still at that point in time, there's nothing more they could do. They had to just open the spillways, and the water just rushed down to the Feather River. And this was a situation that, each of the spillways, the dams, and also the areas around the reservoirs actually experienced a lot of erosion and flooding and other damage. So, for perspective, a few days before this event happened, most of California was mired in a exceptional drought. Remember, exceptional drought's extremely bad. That's when vegetation is dying on a sort of a continuous basis, where you can start thinking about the tumbleweeds blowing through town, so to speak. And a great amount of the region was actually in severe drought. The areas of moderate drought had no precipitation, but were largely being fed by snowpack melt and access to groundwater, which has those other implications we talked about. Just a perspective, that rain event, just moving a few days, basically even through the end of that year, almost all that region went from all Southern California being in some form of drought to extreme drought. No more extreme drought was left, and most of the other region actually was out of any moderate drought by the end of September, or by the end of 2007, based on the fact that we had such a large precipitation event during that time. So again, what caused that precipitation? This is something that I'm going to highlight. You'll see on the third exam for sure. But the big thing is that in the Southwest, particularly in California, the event that's going to cause precipitation is largely going to be controlled by monsoonal type El Nino storms. So El Nino years, flipping to an El Nino, leaving warm water over Central and the west coast of Central and South America, leads to El Nino years, or lead to storms that get to our region. Moving forward, what saved California at that time was actually the presence of strong El Nino that brought a lot of storms to the region. The concern, it's very hypothetical at this point, and I don't think we really know the answer. The concern with folks in terms of when El Ninos occur for the long-term viability of water in California is that El Ninos, in light of climate change, could become intensified. The water could be warmer, like we saw there in 2015, where the water, actually there was so much storm energy, the storms went up beyond California, moved further north before they actually steered on the land. And there's, it's still a hypothesis that we don't know the answer to yet. But the theory is that in climate change, it's not necessarily clear that we're going to be able to rely on these storms to bring water to California. It might be that water is actually going to be coming up into the Oregon area, or in 2015, as we talked about earlier in flooding lectures, is that actually led to incredible amounts of precipitation in the high plains of North Dakota, southern Canada, which actually caused a lot of flooding in that region. Might be good for that area, but the reality is we just don't know. In the best case scenario, areas like California, had a 1 in 7 chance of having a year restored reservoirs. The last 30 years have demonstrated to us that, quite frankly, we don't know that process very well. It's not a very robust 1 in 7 chance. And in fact, if climate change gets much worse, the leading hypothesis suggests the storms are going to be going further north, or if it's at a La Nina phase, not at all. Another point I want to make there is that when people talk about sort of great degrees of climate change, if the whole global ocean gets warm enough, and the atmosphere gets warm enough and wind patterns are distorted, you can actually sort of minimize the gradients of heat transfer, which will also have unknown effects on El Nino and La Nina. So, takeaway points for this is that water resources in California have to be managed really, really effectively, and in many cases, we just basically have to manage them with a mindset towards a 20-year drought, because we've seen that happen very clearly in the last in the last 25 years alone, where you can see a 20-year drought, for extended period of time, so that drought can persist without any clear pathway to providing water resources to the area. Here in that particular instance, several years of snowpack caused by dryness during the sort of fall. And I should have said this earlier. The reason snowpack is additionally so important in the area is most of the wet season comes in sort of October to December. So it's a period where the storms come through the Sierra Nevadas. They're going to lead to snowpack. But several years of low snowpack caused, largely by absence of storms and climate change, led to great depletion of the reservoirs. People had to continue on their lives and continue on developing crops and whatnot. So they did groundwater withdrawal. It's astonishing to realize areas where it's been, basically drawdown of aquifers and subsidence on the order of 20 feet. So you actually, or more in some locations. You can actually go there in areas of withdrawal, and you can see a well, a big pipe sticking out of the ground with a wellhead on top of it, just like you see in a, if you've ever seen a well on a farm or a rural area. And there's actually ladders up to start using the well. The well's still now above the surface of the ground because the ground has fallen around it, which is quite a shocking thing to see. The good news, update in terms of 2017, the reservoirs were replenished. How well we are going to do with managing groundwater resources is sort of unclear and difficult to access. I think the reality is there's a lot more attention to it, so people are doing a bit better. But just to give you a perspective on this, we're only at year 2020, and already we're of course seeing an absence of replenishing rainstorms. Maybe we're not due till up to 2024 would be the long-term statistical average of one event in the next 7 years. But bottom line is we're already going back into those drought conditions. And from the macroscopic perspective, what's scary is that during that time the population in those areas has continued to expand, agriculture has continued to expand, water use has continued to expand, and that's true of Arizona, New Mexico, California, Nevada. All the areas have continued to see population expansion, going back to our core theme of sustainability that we talked about beginning of the semester. We're gonna switch gears a little bit, although it's still very relevant to the California water story. But the other aspect of how most of this region, with very unreliable sources of water, with high susceptibility to prolonged drought and poor forecasting for precipitation events, the long-term story that's led to this area seeing this population growth is actually tied to sort of a American development process in the early part of the last century, where we basically explored things like the Grand Canyon and the Colorado River, and we came to the decision that one of the ways we could try to develop this vast desert region with very poor access to water historically would be by taking advantage of the high amounts of precipitation and snowpack melt in the Rockies, and basically that water that's sort of naturally flowing down the Colorado River, headwaters up here in Wind River, area in Wyoming, western Colorado, and all that water normally flows down through the Grand Canyon to the Gulf of California. And basically today this remains one of the biggest water controversies and in many ways controversial decisions. This region of the country has seen great population growth, great agricultural productivity in certain areas, and that's largely because we chose to put dams on the Colorado River and basically create water reservoirs that could be used for both hydroelectric power, but also could be used for water supplies for this area, which otherwise, quite frankly, wouldn't be. Several of the largest cities in the country now, LA, Phoenix, are in this region. They're accessing water from the Colorado River, and we're gonna basically spend what's left in class today and most of next lecture on Wednesday, talking about how the Colorado River has influenced water supplies in that area. So today, to set the groundwork for this, is that the Colorado River is one of the most controlled, well-regulated, mandated water supplies, but also one of the most controversial and litigated water supplies in the world. I made a joke in the lecture on Friday that the sort of Western motto about water is whiskey's for drinking, water's for fighting over. And the reality is that there are myriad of court cases been in litigation since the 1940s about how to apportion and partition the water that comes out of this region to make sure it can be fairly used by folks across the area, which remains a major controversy. In the last lecture, I introduced the folks living on the Navajo reservation who basically have the Colorado River running right through and by their lands, but have had limited access, where other populations like in Phoenix and in Southern California have pretty profound access to it. So we're going to take you through that. It's a useful thing when we think about social justice, water legal aspects, sustainability, or just interest in politics or the hydrogeological systems. It's kind of got everything in it. And often, if you get involved in these issues, it's more driven by lawyers and policymakers than it often is by scientists, I would say. So for perspective on the Colorado River, the basin is huge, nearly 250,000 square miles. If you think about the areas I just mentioned, Phoenix and LA being some of the largest in the cities in the country, but there's not a lot in the Colorado River basin. In terms of population, Denver's to the east, Salt Lake is to the west, Las Vegas is one of the sort of main cities in there that I didn't mention earlier. In terms of cities that are actually naturally on the river, on the Colorado River, there are only Yuma, Arizona, with 42,000 people, maybe about 45,000 now, is the largest town that's actually on the Colorado River. There are only 3 cities with a population of greater than 50,000 that actually are on within the water basin itself. So Phoenix, Las Vegas, and Tucson are actually naturally within the basin, at least. Most of the use of the water actually is over in Los Angeles and San Diego by aqueducts we'll get to later. So the important thing to recognize here is that the time when they chose to start putting in the dams, developing the region, there was basically nobody there. There was an effort to sort of populate this part of the country, develop water supplies for California, which was already starting to grow based on its own merits, but it was really stricken by access to water. So, just to give you a sense of this, the ultimate headwaters in the Wind River Mountains in southwestern Wyoming. The river actually travels about 1,430 miles from Wyoming all the way to the Gulf of California, and it actually encompasses 7 states and Mexico, including Wyoming, Colorado, Utah, New Mexico, Nevada, Arizona, California, and actually into the nation, crosses 2 countries, the U.S. into Mexico. And actually, compared to for how much of the U.S. population relies on this area, the flow through the river is actually relatively small and actually partly seasonal, depending on snowpack melt. So for perspective, the Colorado is about 3% the size of the Mississippi and about 10% of the Columbia River in the Pacific Northwest. So relatively small, but incredibly important. It provides water to about 15% of the U.S. population, 36 to 40 some million people, and that number is variable, not just in terms of the fact that the population is growing, but based on the fact that in given years when there's local snow melt, less of it can be used at different times, stuff like that, based upon how full the reservoirs are in California, for example. So in some cases it can be higher, some cases lower, but it's most importantly the sole source of water for the Imperial Valley in Southern California, which is really this region of agriculture, where water is basically aqueducted to make sure water is there for irrigation. So the southern part of the Central Valley is called the Imperial Valley. It's one of the most productive agriculture regions in the U.S. or actually anywhere in the world. Even though naturally it's very much a desert, you can see now it's actually an entire grid of tiled fields that are very heavily irrigated, actual irrigation ditches, drip irrigation, aqueducts, and all this comes from the Colorado River, to the hundreds of miles to the east of the region. For perspective, the number of dams that water coming from Wyoming will come across 29 dams and hundreds of miles of canals before it's ever used for irrigation, in this part of Southern California. And of course, two of those dams, Hoover and Lake Mead, um, basically create the largest. Hoover Dam and Lake Mead is shown here. Actually creates the largest artificial lake, and it's one of the largest artificial lakes I think in the world, maybe top 3 last time I looked. Um, just to give you perspective, this is actually, if any of you ever heard of the Salton Sea in California, it's an area of my own personal active research. This is right at the southern tip of the Imperial Valley in California. This would be sort of east of the region between San Diego and California. And this is at the bottom line of all those 29 dams, hundreds of miles of canals, bringing this over to this area for the irrigation of this region. And actually, the Salton Sea itself was actually created accidentally when the Colorado River, flowed during a flood stage. The irrigation canals that brought the water from the Arizona California border actually flooded, and irrigation canals overflowed into this valley, and the Salton Sea was actually created accidentally. It was just a dry valley before that time period. So important thing we'll end with for today is that as early as 1922, the Colorado River Compact was signed. Basically, what they did is that time the Colorado River Compact divided the river between between the upper and lower basins, and divided the apportionment of how much water was flowing down the Colorado River up to various states and between the two countries, based upon the population of people using water at that time. So basically, almost 100 years ago, 100 years before the present time, the Colorado River Compact basically distributed the water access around to the different states and between U.S. and Mexico based upon the population of the region where the Colorado River flowed by, at that time. So as a result, you can imagine places like Arizona, which now has Phoenix and is rapidly growing in population, was relatively small compared, relatively small at the time. Doesn't include all the California or Colorado populations, just the percentage live there in that area. But certain states like Nevada, which now has Las Vegas and has seen a lot of rapid expansion, actually had very low populations at the time, before Vegas was as we know, Vegas today was built. And as a result, their allotment of water is actually well below what the water populations are. So water in that region is quite expensive, quite limited, and actually things like Las Vegas, you can make your own value judgment. The growth of cities like Las Vegas are limited by the fact that they had by what their population was 100 years ago, not what the population is now. And it was actually all the way to 1944 until the U.S.-Mexico Treaty allotted the water to Mexico, again using the numbers based on that time. So Mexico actually, in some years during that window, the water was entirely consumed in the U.S. And as a result, there were some years water actually didn't make it to Mexico. Today, there are many years where there's no water that actually drains into the Gulf of California, where there are actually all the water on the Colorado River is entirely consumed by people along the way. So, for perspective, today, because of the relatively high percentage of folks in California at the time, it's relatively good news for the Californians. Today, there's actually the Colorado River Aqueduct provides water to 10 million people living in the LA metropolitan area, and provides enough water to irrigate most of the southern Imperial Valley. Other parts of the country actually have very little access to it, even though their populations have since grown. So just in the perspective of the water gets to LA and to the southern Imperial Valley, that relies upon an aqueduct that runs 250 miles from Parker Dam, which started about 1941. San Diego Aqueduct has its own, was constructed 6 years later as its own separate line, and actually delivers water for about 3 million people. So you can see there's sort of a lot of concerns about the equitability of where the water is distributed based upon, long ago populations. There's been a lot of litigation since then, but very little change. Most of the rules around where the water is distributed to today still depend upon how this was apportioned back in 1922. This is an example of so here's the actual Colorado River border, comes down through here. This will give you an example of the aqueduct systems, which bring the water all the way over to LA, San Diego. So here's Park Dam, and then also to some of the other areas in this region. These aqueducts, the All American Canal, is actually all tied to providing irrigation for the water for the irrigation in the farming districts. Um, this map also shows you the aqueduct systems that come down from the Sierra Nevada snowpack, which um, isn't actually related to the Colorado River. Um, so I'll end with this picture for today, but I want to ask, excuse me, I want to ask, can anyone envision any problems with having such an important water resource and transporting it a few hundred miles along this aqueduct or canal um, in California? Can anyone think of just some obvious things that make that sort of maybe maybe there's not a good solution, but kind of limit the impact? Can anyone take a guess at the long term issues with these aqueducts and canals? Yep, someone guessed evaporation. One of the biggest things is that just like the reservoirs in California, depending on the year, there's 10 to 20% loss of water just by evaporation. So a lot of the water that's intended and critically needed to get to these locations actually is lost by evaporation itself. It's a bigger problem for the reservoirs in California, quite frankly. It also creates some very peculiar property divides, right? Their properties are split up on um, both sides of the aquifer, or both sides of the aqueduct. So people don't actually have access to get across them very easily. So it creates sort of transport issues for livestock, for wildlife, and also someone, yeah, a great suggestion here. There's pretty ample concerns for things like contamination. Um, you know, I saw here the ash from fires, erosion. It's also not particularly well controlled for actual flood events. As a result, the water ends up has to be treated pretty far, many times along the process. So there's a variety of issues. We'll talk about them more on Wednesday, but direct loss of water by evaporation, access for contamination, and then also creating property divides that often split farms up without a in many cases easy access to get over across the aqueduct. Has basically created some winners and losers in terms of property owners in the region. And the Colorado River is a incredibly, as you mentioned, litigious and complex issue. We'll pick up there on Wednesday. I hope everyone has a good week.